Our second speaker this morning is Changying. So he's going to be talking about bi-exact von Neumann algebras.
Great. Thank you, Matt, for the introduction, and thanks to the organizer for the invitation. So today I'd like to discuss a joint work with Jesse Peterson on bi-exact von Neumann algebras. So I'd like to start the discussion by recalling the notion of prime to one factors. So there's one factor, n is prime if you cannot write m as a tensor product of two to one factors. And in general, you say a von Neumann algebra is prime if it cannot be split as a tensor product of diffuse von Neumann algebras. So this is a natural structure question you can ask about any von Neumann algebras, and the motivating question would be find examples of prime to one factors, or just prime von Neumann algebras in general. And I think Greg will talk more on the primeness later this afternoon. But okay, so what are the examples? So the first example is due to Popa in '83. So he showed that a free group with uncountably many generators is prime. So S is a uncountable set. This is an example, but this will not be a separable to one factor. So it takes quite a bit of time to have the first separable example that due to Ge in '98. So Ge showed that the thing you would expect that its free group factors are prime. So I should mention that Ge uses Voigt-Kolaskus free entropy theory to show that free group factors cannot be split as a tensor product. So in this paper of Ge, he asked the following question in the very end of the paper. So Ge asks, is it true that for every diffuse so if we take any diffuse subalgebra inside a free group factor, its relative commutant is amenable. So he asked this question, and the thing to notice is that, so we call this, in this case, so Ge asked if whether it is true that for any diffuse subalgebra the relative commutant is amenable, and let's just say this property is called a solidity. We'll say the free group factor is solid if we satisfy this property. And so the thing to notice is that solidity passes to subalgebras, and also solidity implies primeness. So essentially what he is asking is that if whether solidity plus non-amenability implies primeness. So essentially what Go was asking is that whether every non-amenable subfactor of the free group factor is prime. And then after that comes the landmark theorem of Ozawa. Is that it shows that free group factors are exactly solid, satisfy this property that if you have something diffuse in the thing that commutes, the relative commuton has to be amenable. So you cannot have two large pieces inside free group factor that commute. Large meaning non-amenable. And so I should mention what are the techniques goes into the proof. So the proof is this is based on C-style algebraic techniques. So there are two main ingredients that goes into the proof. So the first one is that due to a result of Ekman and Osram in 75, where they compute the norm of free group, the C-style algebra of free group very explicitly, but it comes down to the following fact. That is, if you look at the reduced group C-style algebra given by the left regular representation, and so here gamma is the free group. So if we look at the reduced group C-style algebra generated by the left and right regular representation, and we look at the following map. I just send A tensor B to A times B. Of course, we're not mapping this into B of H, because otherwise that would imply the group gamma is amenable if we have the mean continuity of this map. But instead, we're mapping into the Changying algebra. So the result of Ekman and Ostrand, their explicit computation comes down to that this map is mean continuous. So it basically says that the free groups are not amenable, but when you are looking at the maps into the Changying algebra, it is somehow resembles amenability. And so, but this is a result about the reduced group cis algebra, but the result of Sakai is about free group factors. So there is another ingredient that comes into play is that the passage from the group cis algebra to the group bottom algebra. So another one is that this is group cis algebra is exact, so it is locally reflexive, and you can use this property to pass to the Huaidu and especially pass to the group bottom algebra. So let me just quickly mention, the ideas of the proof is that, so let's say we have a diffuse subalgebra A inside the free group factor, then we can produce a sequence of unitaries that goes to 0 weakly. And the thing is, if we now apply those unitary by conjugations on B of L2, and because that sequence of unitary goes to 0 weakly, that will kill the compact. So essentially, you will get a map from B of L2 to B of L2 that you can restrict to the Changying algebra. And now you compose that you compose the unitary conjugation by this map here, and because we're taking A, then this map will not interfere with the thing that commute with A inside here. And now essentially what we're going to get is a map from, let's suppose this is a von Neumann algebra here, because that uses the exactness to pass the von Neumann algebra. So essentially what we're getting is that you have a map from A tensor L gamma to B of L2. And now you use the trick is that because we're mapping A tensor M, so you just do the Arvidsson extension that gives you a map from B of L2 tensor, and from B of L2 of gamma to A prime, that gives you the amenability of the relative commutant. So essentially, the thing is that this doesn't really matter is because you're taking the diffuse subalgebra, and that gives you a sequence unitary that kills the compact. And so in this theorem of Ozawa, he didn't only just show that free group factors are solid, and some more is true is that so the class of exact groups satisfy properties 1 and 2. So this class of groups is introduced by Taka, and all of them will satisfy those two properties, and that means that his proof goes through, and they show that he showed that all of them are all of their von Neumann algebras are solid. So before, well, you can take this is mean continuous together with the group is exact as the definition of bi-exact groups, and we'll introduce another perspective on this class of groups. But before getting into the other definition, I'll just give you some examples. So not only just free groups are satisfy those two properties, but also hyperbolic groups, they all satisfy this property. So in particular, you will have some property T factors that are solid. Another example will be SL2Z cross Z2. This is also an example of a bi-exact group. And also you can look at wrist product. So if you take a minimal group and take the wrist product with some bi-exact group, and the wrist product will still be bi-exact. So as you can see that we have a much larger class of groups that gives us solid factors, just beyond the free group factors. And there are some more recent examples, including also, so all of three examples are due to Taka, and there are some recent examples due to Oyakawa, relative hyperbolic groups with bi-exact peripheral subgroups, and also some many small cancellation groups, so they are all bi-exact. So there are more examples. So let me just, so this perspective on bi-exact group is somewhat more algebraic, operator algebraic, and there is another way to think about bi-exact groups. So And so let me describe an alternative description that will be more relevant to what we're going to be doing next. So now let's look at a subalgebra of all bounded functions on group gamma. So this is inside L infinity. This is a C-star subalgebra. So what we're looking at is the collection of functions that under the right translation. So here RT just means that RT of f at G is just f at GT. So this is the right translation action. So what we're looking at is that the functions that are almost invariant under the right translation. By almost, I mean modulo the functions that vanishes at infinity. So we have so you can check very easily that this is a C-star subalgebra. And so, well, you may ask, why do we want to look at this subalgebra? So if we look at, if we think this as continuous function on a compactification of gamma, so we take the Gelfand dual of this, then this gamma, this type of compactification, we can describe this in a universal way. So this is the universal compactification of gamma, such that if we look at the right action of gamma, so we have a natural extension of the left action of the right action of gamma on itself to its compactification. And if we look at the right action on this boundary of the compactification, then this is trivial. So the terminology is that this is the small at infinity compactification. Small exactly means that the right action becomes a trivial action. And here S denotes small. So, okay, so this is somewhat a universal object we can look at, and then how is this related to bi-exactness? And yeah, sure. So gamma is bi-exact if the action, the left action. So this is we have the left action on L infinity of gamma, and you can check that this is actually going to be invariant under the left action. So we can restrict the left action to this subalgebra here. So the thing is that we can recognize a bi-exactness by looking at the left action of gamma on this system algebra. So another equivalent definition would be gamma is bi-exact if only if the left action here is a topologically amenable action. So we actually do have a more topological dynamic characterization of the notion of bi-exactness, or you can think this is a topological dynamic characterization of these two properties together. Oh, maybe I should mention that what I mean by topological amenable action, that just means that this just means that because we have the action, so we can form the reduced cross product, and this is nuclear as a C-star algebra, and this is also equivalent just by looking at So we have a copy of the reduced group cis algebra inside this cross product, and we can just look at the inclusion map of this group cis algebra into the cross product, and it's the same as this inclusion. Inclusion is a nuclear map, meaning that we can find some UCP maps that factor through matrix algebras. So we can find some UCP maps that factor through matrix algebra into the cross product that converges to the inclusion in the point Norm topology. So essentially, the bi-exactness amounts to looking at the inclusion of the reduced group cis algebra into the cross product of the small and infinity boundary across the group itself. Okay, so and remember, this would just exactly mean those two properties. The group is exact, and this map is mean continuous. Okay, so I should mention that since just right after the theorem of Taka, then these lines of ideas and methods are combined with Popper's deformation rigidity, and use many structural results of group quantum algebras. So this notion of bi-exactness is widely applied to many situations, but we'll not go into that in details here. Right. Yes, so now we see that we have this topological dynamic characterization of bi-exactness. So you may think it's somewhat topological in nature, but a result of Sacco shows that 2009 shows that if we have two groups that are measure equivalent, and so if we're given two groups that are measure equivalent, then gamma is bi-exact, if and only if lambda is bi-exact. So indeed, this property, this somewhat topological property, can be recognized through measure equivalence. This is somewhat interesting because this is measure equivalence. And then there is another question you can ask, given the close relation between measure equivalence and the isomorphism of the corresponding group quantum algebras. So the question would be if just replace the measure equivalence with isomorphism of the corresponding quantum algebras. Does this imply that the other one is also bi-exact? So the question would be, if you have two groups that have isomorphic quantum algebras and one of them is bi-exact, and you recognize bi-exactness of the other group through the isomorphism of quantum algebras. And this is the question I want to discuss today. So just like many other group properties that are also quantum algebra invariants, like amenability and the property T, what you usually do is just you try to introduce the corresponding notion for the quantum algebra and show that it actually coincides with the group notion when you restrict to group quantum algebras. So that's what we're going to do here, is that we're going to use bi-exactness. for, let's just say for 2 vectors, and show it with a group notion. So that's what we're going to do next, is that we're going to define bi-exactness for 2 factors and show that it's exactly the same as the group notion when the 2 factor is a group on an algebra. Okay, so what are the things that goes into the definition of bi-exact groups? So we're going to take this perspective. That is, we have this C algebra S gamma, or you can think we have this small at infinity compactification of the group. And we're going to look at the action, the left action of the group on this C algebra. So the first thing is we have this S gamma here. So I drew it there. And the second thing is that, so this small at infinity compactification. So that's the first thing that goes in the definition. And the second thing is that the left action is amenable. So to define the corresponding notion for von Neumann algebras, then we need to find analogs of those two properties. So we will need to find what is the small at infinity compactification of a 2 factor, and also what does it mean for 2 factor to act amenably on some compactification of the 2 factor. So probably now let's look at the first thing. So what is the corresponding thing for 2 factor? So we're in the commutative case, we're just looking at a function space, right? And so there is, you can follow the standard dictionary that if we have m is a 2 factor, and can just try to look at, just replace L infinity of gamma by bounded operators on L2. And the right action will then be replaced by the commutant of M inside B of L2. Right, so that will be a direct translation from the commutative case to the non-commutative case. So we replace this L infinity with B of L2, replace C0 with compact, and replace the right action with M prime, and replace the the conjugation by the commutator. This seems to be fine, but it turns out that this is not the correct thing to look at, because this is exactly just M plus the compact by a result of 75, I guess, or also just proposed by 83 or 87, I can't remember exactly. So that means that this, if you just do the direct translation, then there's nothing to look at. You're just looking at M plus the compact. It's not interesting at all. So that means there has to be something to be modified if this approach will work at all. So what we're going to look at is exactly the same thing, but just do one modification. So this is not the right thing, but So what we do is that we don't take the compact, but we slightly enlarge the compact by taking the infinity one norm closure of the compact in B of L2. So what is the infinity one closure? Infinity one norm, that is just, so usually when you take the norm, you take the soup over all vectors in L2, but now we just look at all vectors that are in unit ball of M. So this will be the infinity one norm, and we're taking that closure of the compact and taking that into our definition of the small infinity boundary. So why does this help? And there are several considerations for taking this closure. The one consideration is that if we just take the compact, then there's nothing to look at because it's a trivial. Skip this. This is a trivial thing. Another consideration is that we're defining the non-commutative small and infinity compactification of M, so we want to relate that to the commutative one, which is S gamma here, and we know that if we all those functions F will commute with our group's element modulo the compact, but how are we going to check this is true for every single element in a volume algebra? So here is the second reason is that so if we have some t inside B of L2 such that Tx is in the compact for x inside x, x is a generating set. And then T will be inside S, or T will be inside this. So you see that this is somewhat a density thing or some kind of closure thing. That is, if we know some operator that commutes the commutator with things in a generating set is compact, then taking this closure automatically gives us that this relation passes to the closure of the, or passes to the whole volume algebra. So you can think this as some kind of, this is kind of some taking closure we can pass to the closure of the generating set. So in particular, we have the commutative one. If we look at all the functions and we look at those as multipliers, diagonal or multipliers on B of L2, then this will be inside S of L gamma. That's just because by definition our F will almost commute with the right regular representation, and those generates the R gamma. So this taking this closure is essential because that allows us to show that we do have a embedding of the commutative boundary into the non-commutative boundary, just through the multiplier map. And another consideration would be, another thing is that if we just take the conditional expectation from B of L2 of gamma to the diagonal L infinity, then this will restrict to a map from the non-commutative boundary to the commutative boundary. So that's how you relate the commutative one with non-commutative one, is that one embeds into the other and the projection takes the non-commutative one to the commutative one. Okay. Yes. And So that is the first part. That's the part one about the small infinity compactification. And the second part will be looking at the corresponding analog of minimal actions. So we're taking the perspective of the group C algebra inside the cross product. So if we think the cross product as the non-commutative boundary, then we're just looking at the inclusion of the algebra into the cross product. And here, this S of M, you can see that it clearly contains M. And so what we're being looking at will be the inclusion of M into S of M. So I should mention that this S of M is not a C-state algebra just because we're taking this infinity one closure, and the infinity one closure will not be a C-state algebra. So, but this will still be an operator system, or we can look at the inclusion of M into this operator system that contains M. So in the group case, we have that we're looking at the inclusion of C-state of gamma into the closure of, into the cross product. And we know that this is characterized by biexactness is characterized by the factorization of this map through matrix algebras. And now, how to make sense of amenability, amenable actions in the volume algebra setting? That will be, we're looking at the inclusion map of M into this boundary S of M, and to say that this is nuclear in some sense, some appropriate sense. So there are some natural candidate that will be, you look at the norm topology, or you think this is norm nuclear, but that will be too strong for volume algebras. And there is another one will be look at point Weak-Star convergence. That seems natural for volume algebras, but the thing is that this is not a Weak-Star closed subspace of B of L2 because it contains the compact, and if it's closed, then you're just looking at into the B of H. So there has to be in some sense, there has to be in between the norm nuclearity and the Weak-Star nuclearity. So some kind of norm and Weak-Star hybrid thing that's going on here. So what we're going to look at is the following space of functionals, because the norm nuclearity can be characterized by looking at all the functionals on this C-state algebra. So we can look at the following space here. So we'll just be looking at a subspace of functionals on our operator system or our boundary of M, such that this is so we're not looking at things are normal on the whole thing, but we're looking at things that are normal. So if we have x and y inside M, then we can look at x times t times y when t is in our S of M. Then we're just looking at all the functionals that are normal. When you fix a t and fix a y, then it is normal for x. So you can think this as a normality condition on the bimodule structure of M, because they're normal when you look at things multiply on the left and things multiply on the right, but it will be the norm topology on the thing that from the boundary here. And now the nuclearity would just be that nuclearity is exactly the same thing, but we just modify the topology. And the appropriate sense is that so phi and Ci, there are UCP maps such that if you look at phi of, so it just means that we have the composition of phi and Ci goes to the inclusion map or identity map on M in the point sigma S of M and S of M sharp topology. Right, so if we replace the sharp with everything, or replace sharp with star, then it would just be the same as point norm convergence. But now we just do a little bit of a restriction to say that we only look at functionals that are placed well with von Neumann algebras. And the definition will exactly be that M is bi-exact if the inclusion is M nuclear, and the M nuclear just means that we have nuclear maps. We have maps factored through matrix algebras, but the convergence is in the sharp space. And we call this M nuclear because the sharp space depends, you can see the definition of the sharp here depends exactly on the normal topology of M. So that's this convergence depends on which von Neumann algebra you choose. For example, if you choose M to be the scalar, then that will exactly be the norm nuclearity. So it's an M-dependent definition. So if this, and you can see the analogy here is that let me just go back to the group case very quick again. So the group case we have that this is the cis algebra into the cross product. This is nuclear in the norm sense, or in the wake topology sense. So this is same as gamma is bi-exact. So what we're doing here is just replace the group cis algebra with the group von Neumann algebra, and replace this cross product with the boundary we just construct, and replace the nuclearity, the factor through matrix algebra with this not just looking at all functionals, but looking at functionals that are respect the Biexact topology on the von Neumann algebra. This is nuclear, nuclear. So I hope the analogy is so I hope that by looking at the group case and the group von Neumann algebra case, I hope the analogy is clear. So they're essentially the same thing, but you just do the modification that essentially you want to respect the normal structure around the von Neumann algebra. And let me just quickly justify the terminology here. That is why it's sensible to call such a von Neumann algebra bi-exact. So we're going to give you a sketch that the group is bi-exact if only if the group von Neumann algebra is bi-exact. So one direction, so if you know the group is bi-exact, so our characterization here is that this inclusion is nuclear map. And the thing is that we know that this S gamma contains inside the non-commutative S of L gamma, and the containment is a gamma equivariant inclusion. So this will give us an inclusion of the reduced cross product into the non-commutative boundary. So what we have is that we have a nuclear map from the group cis algebra to the boundary we just construct. And now you can use local reflexivity to pass it to the Von Neumann algebra into S of L gamma. But you have to change the topology. So this is L gamma nuclear. So one direction just comes from the construction of the boundary, and we have the cross product inside the boundary. So, and we also use local reflexivity to pass from cis algebra to Von Neumann algebras. So one direction, that's one direction. Now, what about the other direction? So the other direction is also not very hard once we have the correct notion in hand. So let's suppose we have, so the other direction is that suppose we have vi factor through matrix algebras. And now back to the boundary for Von Neumann algebras. Remember that we mentioned that if you took the diagonal map from B of L2 to L infinity, that will give us a map from the commutative boundary to the non-commutative boundary to the commutative boundary. So we just compose with this diagonal map. That gives us a map from L gamma to the small infinity boundary for the group. And now you can just restrict this, you can just restrict this map to, well, not exactly this map. But now you can define a map from the group gamma to the cis algebra S gamma, just given by this map here. So hi of t will just be E of Ci composed with Phi, and you just have this is lambda t star. So what we're doing is that we just take lambda t inside of our gamma and factor through matrix algebras, and then project that down to the commutative function space. And in the process, we multiply by a lambda t star. So this will be a map from gamma to the function space. So this is positive definite because all the maps are UCP, and this is finitely supported because we're factoring through matrix algebras, and hi goes to the identity in point norm topology. So this net of functions goes to the identity function because this, if Ci phi applied to lambda t is really close to lambda t, then this is just 1. So so by this this converges to the inclusion map, we have that this goes to identity function, and this is exactly the Foner type characterization of amenable actions of a gamma on a commutative cis algebra. So that shows that that gamma x on this is amenable. So that shows that gamma is bi-exact. So that will be a sketch that why this notion makes sense. So let me just quickly mention one consequence is that you can show that this notion of bi-exactness from Von Neumann algebras passes to sub-algebras quite easily, and then a quick consequence would be that if L gamma, if you can embed a group factor into the free group factor, then gamma is a bi-exact group. Okay, so I think I will just stop here. Thank you.